Hey guys, all right. Let's keep going on our third unit here. So this is lesson 2 of unit 3. Um, we're talking now about the electric field. So previously we talked about Coulombs Law, which defined the electric force felt by two charges. Right, so that implied that there's two charges and that they have to feel some sort of force in between. Right, and the law of electric charges. We already learned that in grade 9, and we talked about how Coulombs law is basically the law of electric charges from a mathematical point of view. And here, this is what it looked like again. K, Q1, Q2, all over R squared. So again, it's a inverse square law. It's like gravity. Instead of masses, we have these charges, Q1 and Q2. What we want to do now is take this idea of a force between two charges and apply it to the force on one charge. How does that make sense? How does that make sense that we can have force? Don't we need two things in this equation? Yes, but we want to talk now about what the influence is from a charged object all around it. So instead of having two charges, we're going to take just one charge, and the second charge we're going to call a test charge. And we're going to use a positive test charge. Very important that it's positive because that implies, that tells us which direction all of our arrows are going to be. And we're going to use a value of 1 coulomb, which means you don't have to worry about it influencing anything. Because when you multiply by 1, nothing happens. And so we're going to use 1 coulomb positive, and we have our test charge. And we're going to move it all around. So let's say I have, here's the die. Okay, so this is our charge. This is our Q. And it's just floating in space. And I can assign to this point here, this charge, a value. And let's set this a reference point. This will be my origin. And I'm going to pick a point somewhere here, let's say, and I'm going to calculate the force felt here on 1 coulomb. And that's going to define, let's say this is positive, it's going to define some arrow that shows the force there. Now I'm going to take my test charge and move it somewhere else, and it's going to give me a different arrow. And then I'm going to move it somewhere else and a different arrow. And I can do this everywhere around it, and it's going to give me a whole bunch of force values everywhere, and it's going to tell me the electric field, the amount of influence that charge, this charge here, actually creates around it. Okay? This is a fascinating idea that we're defining what we call a vector field that represents all the force felt around that one charge Q1. Mathematically, it's really fascinating because we are now going from a three-dimensional view. So let's say we have our charge here. This is in 3 dimensions. So anywhere in this volume, you're going to define a point x, y, and z. Right? That'll define its position according to some Cartesian coordinate system around in 3 space around this point, origin here. And to that point, I'm going to define 3 new numbers that'll define this vector felt at that point. So this will now have 6 variables at that one point. It becomes a 6-dimensional problem. What's beautiful about this is n-dimensional problems behave just like 2-dimensional problems, just behave less like 3-dimensional problems. The laws of algebra for all of these different types of things at any number of variables are all the same. So we can apply the same laws that we apply for a regular algebra that hopefully you guys will learn vectors right now to multi-dimensional things. It doesn't matter. Just because we can't picture it in our heads, we can still define 6 numbers. And that will define, not only that will define a volume that has a whole bunch of arrows everywhere in it, and it defines the influence caused by that one thing. Now, that's very theoretical, and it's hard to imagine. So let's go. I'm going to jump here to a simulation here from this PhET website from the University of Colorado. This is on our Weebly. You guys can play with this. Please go play with it. Add some charges and see what happens. Okay, so let's take a positive charge. I'm going to take positive 1 nanocoulombs. I'm going to stick it in the middle of my screen. You know, important note, this is positive. When I take my sensor here, this is my test charge. This is a positive test charge. If I put it here, it generates this arrow. This arrow represents the Coulomb force, the electric force felt by this positive test charge of 1 nanocoulomb. See if it'll tell me. This is going to be 15 newtons per coulomb. It says this weird units volts per meter. We'll talk about that next lesson and we'll talk about electrical potential. But this is equivalent units of newtons per coulomb. Okay, so this now feels an intensity of 15 newtons for every coulomb of charge that I could put here. And if I move it away, it gets smaller, because it's an inverse square law. If I move it closer, it gets bigger. So along this line, I can already generate all of these vectors. Even in this one-dimensional system, moving this back and forth, I actually have a two-dimensional system, because every point along that line has an associated vector magnitude attached to it. Or I can now take this and move it in 2 dimensions. And if I am able to go around in a circle, it's actually kind of difficult, I can try to keep this arrow the same length. So we can show that this is symmetric. There's a symmetrical influence by this one charge. I can move it all over the place, and I can generate an infinite number of these little vectors in these infinite number of spots. Now that's very difficult to visualize all those infinite numbers of things. So instead, let's just make a grid of them. We can imagine now this grid of all these little points, and at each of these points, they're going to generate this little arrow that represents the direction of the force, and how bright it is, how white it is, tells us how strong the influence is. Well, I can move this charge around, and you can see how the electric field changes all over the place. Notice that it's always going outwards because we're using a positive test charge as our reference. So we're always going outwards. If I defined that my test charge to be negative, it would be always going inwards. Okay, so that's a positive charge. What about a negative charge? What's that going to do? Oh, they're always going to go in because those positive charges will always be attracted. I can move this around and keep changing my vector field here, my electric field generated by that. Or I can add a bunch of charges. Let's put 2. Now you can see that the electric field is leaving positive charge. It's going outwards, and it's going in to the negative. Okay? Electric fields always are going out or in from charged objects. That's one of Maxwell's equations, actually, in English. It's write it out mathematically. It's very complicated, but we can just simply state that Maxwell's first equation states that charges either are going out or in from charged objects. Okay? And notice these field lines, if I connected all these arrows into these lines, they'd never cross. Okay? And I can add more. Let's add some more. Happens. Oh, it gets stronger on that side. Right? And you can see this influence is less on this side. More stuff coming out, but all of it comes in over there. Okay? So please go on the website. I invite you to go play around with this. You can even look at something called voltage, which is a potential. See what happens if I put that on. There we go. See that. We'll talk about, we'll play with this again in lesson 3 and see what happens. But I just want you guys now to use this to visualize what an electric field means. Okay, so we can have only one charge. If I reset here, if I have only one charge, I can generate now an electric field, which is the sort of influence in this 2-dimensional space here caused by that one charge. Right? It's difficult to visualize, and it's a conceptually difficult idea, but give yourself some time to think about that and play and see what this one charge, how its effect on this 2-dimensional space changes. Okay, this is making what we call a vector field. Let's go back to our slideshow. Okay, so Mathematically, what we're going to do is we're going to take our Coulombs law. Let's make it a vector now. Remember, we can apply this little r hat, which is our unit vector in the r direction, facing outwards. Outwards if it's positive, right? And inwards if it's negative. So buried in here is, this is the piece that really tells us the law of electric charges. But anyways, let's ignore that for now. Now, instead of doing Q1, Q2, let's say QT here. QT is the is our test charge, and we're going to divide both sides by QT. So now we end up with this idea of force per test charge for 1 coulomb. Newtons for 1 coulomb is defined by KQ over R squared. And this piece here is what we're going to define to be the electric field. Now be careful, this is not energy, this is an electric field. That's why when we did energy, I like to use K and U to differentiate between these, because E is used usually as the electric field. Okay, so the electric field is now defined to be KQ over R squared, and again, it's in the R direction. Or to make our life simpler, let's just take the magnitude, and it's just KQ over R squared. Right, so this is the influence. Now notice this is everywhere. This is now a, let's say in 2 dimensions, this is now a 4-dimensional thing, right? Because it tells us, actually it would be 3 dimensions because it's directional. So it tells us the strength of the electric field at any point around it. So it generalizes the Coulombs law to now an influence caused by a charge. And again, here's just a couple of pictures that show us the charges, if it's positive, they're always having electric field lines going outwards, and if they're negative, they're always going inwards. And you can see here that they're going to leave the positive and into the negative. Or if they're both the same charges, now you can also think about this in terms of attraction and repulsion. Because they're leaving the positive and going to the negative, these are all the forces, the force lines. But really, we're looking at an attraction here, because this positive charge is going to want to follow those force lines and head in this direction. All the ones in these ones, if they're not along that line, the vertical components of those vectors are going to cancel out, and we're going to get an overall force over that way. If they're the same charge, and since the electric fields can't cross, we actually end up with sort of like an asymptote where all these lines approach from both sides. And in this case, all these force lines are going to even out, cancel each other out, and we're going to end up with a repulsion. Okay, so now we can even think about attraction and repulsion and Coulomb's force from an electric field point of view. All right, let's try an example here. Let's go for a little bit more complicated. Let's do 3 different charges. I have this box here. D does not have a charge in it. Well, it does really. It says 1 coulomb test charge, positive 1 coulomb test charge. And we're going to try to see what the influence is, what the electric field is at this point D. So first step, let's define ourselves a coordinate system. Okay, not just that, let's define ourselves a north, south, east, west. And to make our lives easier, we're going to define this positive and south positive, east negative, and north negative. Okay, that's because I can see that A and A are both positive. Well, let's just not worry about it for now. Okay, you'll see why it works out nicely. Okay. All right. Okay, so we have this idea. Now let's break this up into 3 different electric fields. They're all going to be vectors, right? And then we're going to take all those 3 vectors and break them up into components, add up the components, and come up with a total electric field intensity. Okay. Now, I kind of don't like that it says intensity here. Let's just go with electric field, because intensity kind of defines a amplitude, just the magnitudes, right? So let's not worry about that. Let's just find the actual electric field there. So we actually make this a vector quantity. All right, so first step, let's look at the electric field caused by A on D. Okay, so the electric field that is felt at the point D, our test charge, but caused by the charge A. So that's going to be K QA, charge A, divided by the distance to A, all squared. So that's 9, excuse me, rearrange here, 10 to the 9 Newton meters squared, Coulomb squared, all multiplied by 3 microcoulombs. And the distance was 0.06 meters. All that squared. And this is going to come up with a pretty large number. This is 7.5 million newtons per coulomb, or 7.5 times 10 to the 6 newtons per coulomb. And you may think that's an incredibly large number, but it really tells you that 1 coulomb is a very, very big amount of charge. Okay, and also notice I haven't defined this as a vector yet. I've only done this as a scalar. So at this point, why don't we then just put a vector hat on this and say which way. Okay, so let's stop in a second. Let's go back to our picture. Remember, this was a positive test charge, and this A is positive. So there's going to be a repulsion in this direction. There's going to be an electric field. Let's call this AD. Okay, that's going to be pushing it away. So I can say that this is going to be south. Or, just to make my lives easier, I'll actually do something a little funny here. I'm going to say 7.5 10 to the 6 newtons per coulomb. And I'm going to say this is in the y direction, the y hat. Right? So this is E, the vector, the electric field vector, EAD. Okay? Now this y hat, this is a unit vector in the y direction. And I'm keeping this as positive because I've defined down this way, this direction here, to be positive. Okay? So that's my first one. Let's do it again for B on D. So that's going to be the Coulomb constant, charge B divided by the distance to B all squared. So that's going to give me 9 times 10 to the 9 Newton meter squared per Coulomb squared. I forget. -4 minus 4.0 microcoulombs all over 0. What's this distance? So 6 times 6 is 36, 72. So this distance is going to be root 70. Something like that. All right, so this is going to be 0.0. I would calculate this right. 4849 meters squared, which is going to give me a value of 5 million newtons per coulomb. Remember, also scalar, so let's make it a vector now. What's it going to be? This will be, let's go back here. Notice this is negative. Remember, this was a positive test charge, so these are going to be attractive. There's going to be a force this way. Electric field B. So that's going to be in the northeast direction. So, north 45 degrees east. Now, that's okay because it's a vector, but it's not broken up into components. And this is where you're going to see why I use this x hat, y hat notation. Because I can rewrite this as a combination of, it's going to be 5 times sine of 45 or that would be root 2 over 2, or 0.707, where it ends up working up to, now I'm going to call this negative 3.54 times 10 to the 6 newtons per coulomb in the x direction. I'm also going to have negative 3.54 is 10 to the 6 newtons per coulomb y direction. Okay, so I can write this now using this hat notation. I can actually write this as a sum of two vectors. And since the two vectors are at right angles, they don't influence each other, we're good to go. All right, so this is another way that you can write the electric field by B on D is now equal to this expression here. And we can do the last one, C on D. So it's just electric field, C on D. And again, K U of C all over the distance to C squared. Now I'm just going to skip a step here. This is going to be 1.25 10 to the 7 newtons per coulomb. And C is to the right of it, so it's the positive positive. There's going to be a repulsion felt by D. Okay. So I'm going to call this positive 1.25 in the x direction. Okay. Here I have my three vectors I need to add, and since I already have them broken up into components, it's quite straightforward that the total in the x is just going to be, which one's an x? I have an x component here, and I have an x component here, so it's going to be 1.25 times 10 to the 7 newtons per coulomb. Take away 3.54 10 to the 6 newtons per coulomb, which will answer here of 8.96 10 to the 6 coulomb. So that's going to be my x component of my final electric field. And alternatively, doing the same thing for y, which were my y components. I have 7.5 and I have negative 3.5. So 7.5 times 10 to the 6 newtons per coulomb. Take away 3.546 coulomb. This is all in the y direction. End up with the final answer here of 3.6 10 to the 6 per coulomb in the y direction. And this is in the positive y, or south. Okay, so I have an EX and EY. I can now use Pythagorean theorem to find my total. So the magnitude, I'll square those, add them up, take the square root, I end up with 9.6. Right, 9.8 is 10 to the 6 newtons per coulomb, and my angle be inverse tan. I'm sorry, I don't have very much room here. Of 3.96. Can you see that? Yeah. 8.96. So 24 degrees. So there's my final answer. Then why don't I just get rid of these? Final answer is going to be this, and it's going to be mostly in the x direction, so that's going to be west, and 24 degrees south. Okay, there we are. Our final answer. Ooh, that got a bit messy, didn't it? All right, so what do we have to do? Let's recap here. I had to find the force caused by, the electric field caused by A, electric field caused by B, electric field caused by C, and then I broke them up into components, added them up, and got my final answer. Okay? All right. Now, these questions do take some time because you have to end up doing a bunch of different Coulomb calculations and then doing a bunch of trigonometry to make sure you get it all in the right direction and you get the right answer. But they're pretty straightforward once you get the hang of it. Okay? All right. So I'll leave you guys now with these 5 problems of calculating electric fields caused by charges. Okay, answers are there. I will post them online. And good luck and all the best. I hope you guys are all still staying, mostly sane and surviving all this quarantine stuff. Not working too hard, you essential workers. Okay. So take care of yourselves. Remember, stay safe, stay home, do physics. All right. Best of luck, and I'll talk to you later.